Now, what I want to say that diagonal morphism. See, as a consequence of this product, you have some natural map. I can abstractly define diagonal map as a morphism, because you take this identity map. So, what does the theorem product says? That x cross x to x, there is a map. This is a projection map P1 and P2, and there is a map, unique map H. But then you call that delta. You take this identity map x to x, you have this projection map x. You know now for any affine varieties or quasi affine varieties, product exists. So you have this map P1 and P2. Now you take this identity map x to x, x to x. So what does the universal property of the product says? That you have a map from x to x cross x. You call that your diagonal map. That is your definition. So good thing is that you can do it for any abstract variety, pre-variety, or so if suppose you have any category where product exists. So there is a canonical map, the object A to A cross A, whenever product exists. See, giving a global morphism is always a difficult, right? But this is how you give a map. Global morphism, because there is no coordinates, but this gives you a canonically a map, right? And this is called diagonal morphism, right? And when x is affine, the coordinate ring of product x cross x. So sometimes I will write k, because the x and x is a k variety. So this is nothing but ax tensor ax. Our product ax cross y is ax tensor ay. So proposition. So I will not prove, but this you check yourself in the category pre-variety. The way we define what is a pre-variety. Pre-variety, if x is a pre-variety, then it is union of ui's, where ui's are affine varieties. Now for you, so now if you take x cross x, so what will be? It will be something like ui cross uj, right? X cross x, it's like, but product of affine varieties are affine varieties. So this is the atlas for that. Right. So this is how it's a pre-variety. Why it is a pre-variety? It is a very rough way of proving. I was saying you need to make it more rigorous to complete the proof. But this will be the candidate, because ui is a affine variety, uj is a affine variety, ui cross uj is a affine variety. So this is the union of those. So locally it will look like ui cross uj, x cross x, and that is why it is a pre-variety. So in the category the product exists. So that so now the yes, then yes, x cross s is this. If x is union of ui and y is union of vj, then x cross y will be union of ui cross vj. But that is fine, because vj, ui and vj's are affine variety. The product is defined. Yes. And that's also a projective variety. The point is that is also a projective variety. Product of affine varieties are affine. Product of quasi-affines are quasi-affine. So product of projectives are projective. Product of quasi-projectives are quasi-projective. So product really goes well with the varieties. So I will write it as proposition. Product of quasi-affine is affine. Affine is affine. Projective, quasi-projective, pre-variety, this is the most general object, pre-varieties. And now what I will define today, what is called variety, abstract variety. So far we know what is a pre-variety. So abstract variety definition. No, special case. So, but before that, let me say some examples that if you take Pn and Pm, what is the product? So, you have a map to Pn plus 1, m plus 1 minus 1. The map is like x0, x1, xn, y0, y1, ym goes to x0, y0, x0, ym, x1, y0, xn, ym. So, here you have n plus 1 coordinate, here you have m plus 1 coordinate. So, here you have n plus 1 times m plus 1 coordinate, but 1 less, right. And the image, so this map, if I call this I, this map is injective, I is injective, and the image map, image of I is nothing but so if I call xi yj, if I call this variable as uij, so okay, let's I is injective and image is some closed subsets of this coordinate. For example, so let's try to do one for when n equal to m1 and m equal to 1, let's write that for, so here it is p1 and here you have p1 and here it is n plus 1, so 2 into 2 minus 1, so p3. So here you have x0, x1, here you have y0, y1, then you send map to x0, y0, x0, y1, x1, y0, x1, y1. And if you call this u, v, w, s coordinates, then image, we call it I. So I is injective and image of I, this is nothing but x0, y0, so us equal to vw. Zero set of this. This is a homogeneous polynomial, us equal to vw, and this is the zero set of this is nothing. So what are the varieties here? The zero set of some homogeneous polynomial, right, in P3, and this is the hypersurface, is a degree 2 homogeneous polynomial, and this is a projective because this is reducible. Right. So this is the product P1 cross P1. It's embedded into P3. Okay. So now the definition what I wanted to define. So definition, a pre-variety X is called a variety. So X OX sometime, but sometime I will not write OX, the structure sheet X. If for all pre-variety Y OY and all morphisms F hash G hash. So Y is so there is a map F and this is a map G. The set Y, the set of all Y such that F of Y equal to G of Y is a closed subset. This is like Hausdorffness, yes. Separatedness basically. So the analog of Hausdorffness in algebraic variety is called separatedness. Yes. Yes. Yeah, there are. Yeah, I gave example, right? When you take two lines, A1 union, you take the point out. That's open subset, and take the identity map. Then what you will get a point, double point. This is not a variety, because if when you take the this point, where will you send? You have two choices. Separatedness will be. So whatever we work with, most of them we will say that they are varieties. Okay, so take Y to be X cross X. So if the product exists and you take F equal to P1 and G equal to P2, so you have this map X to X. This is P1, this is P2. So then, so now the proposition says that, I'll just complete with this proposition, that X is a pre-variety then X is a variety if and only so delta X always defined, right? Yes, no. So delta X is always a subset of X cross X. If and only if delta X, which is X cross X, is closed. So you don't have to do it for all. See, when you define a variety for all Fg, definition of a pre-variety means what? That for all Fg, this Fx equal to Gx, the set of all point for all y. What it says that you just do it for one map, x going to x cross x, and where you see that there is a canonical map which is diagonal map, and you check whether the diagonal map is closed or the image is closed or not. The proof is just one line. So you have this map f comma g. So suppose you have map fg from x to y. So that will give you a map, product map from y to x, y to x cross x. Basically, y goes to f of y and g of y. Now this is a morphism. because if you take first projection, see, map between y to x is a morphism. If you take the projection maps, they are morphism, but that is morphism given. So this is a morphism, right? So now we take this delta x, which is a subset here. If this is closed, the inverse image is basically the set which you want. So the inverse image of a closed set is a closed because it's a morphism. Y is any variety. So you want to prove that if delta x is closed, then it is a variety. So suppose you have a map. So that means for any map fg from y to x, you want to show that set of all y such that y equal to gy is closed in y. Huh? No, that is the definition. That is the definition of a variety. But now I am saying that if delta x is closed, then this is a morphism. The inverse image of the diagonal in x cross x is nothing but the set which you want, and that's closed because this is a morphism. And the opposite is, now what about the opposite? If this is true, so in particular you take f and g to be identity, then what is fg inverse of delta x? So that will say that it is closed, right? The opposite is also true. So this says that, so this is now the abstract definition of a variety. The pre-variety where the diagonal is closed. Diagonal map always exists because there is a product. So this is the best definition of a variety. It's a pre-variety where diagonal is closed. So I will just write down. So a variety is a pre-variety with where delta x is a subset of x cross x is closed. So this is my definition of an abstract variety, and this is basically the separatedness. When you do scheme theory, you will see the separatedness. There is something called separatedness. When a scheme is separated, this will say that a separated finite type integral scheme is a variety.